All good. Over to you to introduce.
So good afternoon, everyone, online and in person. So it's a pleasure to welcome Ian to the university. He's Associate Professor at HWU, and we met in one of those really awkward NERC things where they get you together and say, talk about your subject. And it's really awkward, but actually it's worked out really well. We supervised PhD students together, and actually this water world in Scotland is quite a small one. So you meet the same people over and over, but it's just really nice to get to sit and hear about his work for an hour. So without further ado, I'll pass you over.
Okay, right. Thank you very much for inviting me to come and present my research here. What I wanted to talk about today is my work on natural flood management or nature-based solutions with regard to hydrology, and just have a reflection on where we are in the field and what some of the needs might be going forwards, and to use my research to illustrate some of these points. Just to acknowledge the work that I'll be presenting is work done by previous members of my group, Dr. Victoria Coates and also Simon DeVille as well. So I just wanted to start by giving an overview of my overall kind of research interests before I then kind of zoom it down into kind of two particular projects that I want to talk about. And this just highlights like how flood management in the UK has evolved over time. So previously it was kind of all focused about land drainage, getting water out of catchments as quickly as possible. That transitioned into protecting the settlements downstream with engineering solutions predominantly. And then my research interest is kind of the evolution of this into a more kind of broad suite of flood management measures that can be used. So some of my work thinks about how we can become more resilient by working with stakeholders and thinking about flood warning systems and forecasting using machine learning techniques. And my work is also both in urban and rural areas, so thinking about how this links to the planning process as well. But my main area and what I'm going to talk about today is my work on working with natural processes. And like I said before, this is relating to both rural catchments and also sustainable urban drainage systems in urban areas. So just as an outline for my presentation today, I'm going to start off by defining what natural flood management is, and then explore two particular problems which have been investigated currently, and then thinking about what this might mean for future research in terms of targeting natural flood management in catchments going forwards. So the two kind of case studies I want to use are thinking about how soil compaction in agricultural landscapes is not homogeneous, it's very variable. And what does that mean for where water flows over the landscape? And also, what does it mean when we incorporate that data into hydrological models? And that links to the second point there, thinking about how we can upscale from very local scale interventions to thinking about how effective these solutions might be to catchment scale flooding. And then I'll end with some brief conclusions. So to start, just defining what natural flood management is. So these are measures that protect, restore or emulate natural functions of catchments, floodplains and rivers. And it covers a broad spectrum of different types of nature-based solution in rural areas. So for example, how soil can be managed in agricultural landscapes, particularly arable and pastoral fields. And I'll be talking about that a lot when I go into the compaction work that we've done. Other examples that I won't be talking about today, but also under that umbrella of natural flood management are planting trees, also wetlands and remeandering of river systems, and also woody debris dams in the river channels themselves. And the key here is thinking about how they impact upon the natural hydrological fluxes in the system and the stores in the system, to see how they all combine together to give the overall effect at the catchment scale. So moving on to the first part of the work that I'll be presenting today, thinking about soil compaction and how this occurs in agricultural landscapes. So the general definition of soil compaction is the process by which soil grains are rearranged to decrease the pore space and therefore the amount of space for water to be stored. And that is often measured and quantified by thinking about the bulk density of the soil, along with other measures that I'll be talking about today. And this figure here, adapted from O'Connell, is a really good example about an area that is not compacted and one that is compacted in the figure on the right there. And how that affects the fluxes of water in the system. So when we don't have any compaction, we get infiltration of water to significant depths into this permeable soil and reduced runoff over the surface. But then when we have soil compaction occurring, this reduces the amount of infiltration occurring, getting more lateral flow, both through a perched water table and also over the landscape surface as well. So this is kind of summed up in thinking about its effect on flooding in terms of the speed of these different pathways. And as we partition rainfall into the overland pathway more than the subsurface pathway due to compaction, that speeds up the time that it takes for water to get to the river channels, and that results in higher peak flows downstream. So these are just some general statistics of why soil compaction is important in the UK. Obviously, it's a really dominant land use and important to the overall economy. But then these statistics at the bottom also show what impact they have on some of these outputs as well. So soil degradation can cost between 0.9 and 1.4 billion pounds per year in England and Wales. 400 million of that is caused by soil compaction alone. And then thinking about the consequences for flood management and flood damages, this is often 168 million pounds per year. So this is obviously causing significant impacts throughout the whole of the UK. And under the current economic situation, building higher and higher flood defences isn't really a way in which we can solve the flooding problem. And then also soil health is also degrading as well, impacting upon outputs from agricultural systems. So that's why we thought it was important to look at the effects of soil compaction and link that directly to the effects on flooding. And to do this work, we studied two particular catchments in England. The first of which was in Yorkshire, the River Skell, which flows down to the city of Ripon there. And this is a catchment area of around about 120 kilometres squared. And you can see there some characteristics of the catchment, and also that Ripon has experienced significant floods since 1982 as well. So that kind of shows that this is a problem in the town, and that the flood defences that have been built haven't completely solved the problems in that particular area. And the other catchment of a similar size is the River Sense in Leicestershire, having similar characteristics to the River Skell example. And there you can see how about half of the catchment, equal proportions, are under arable and pastoral agricultural systems. So that's why we have studied both of those types of agriculture in the work thinking about soil compaction. So the overall aims of this work were to firstly assess what the impact of these agricultural land management practices are, particularly on the soil structure, thinking about the effects of soil compaction. And then secondly, thinking about how that links between the field scale variations and the overall catchment scale flood risk. And just breaking that down, we have identified these kind of tasks. Firstly, to identify the spatial variations in compaction levels in agricultural fields. Secondly, link that to the different causes of that compaction, be it pastoral or arable agriculture, and then evaluate how representative this field data is in terms of catchment scale variability and what impact that might have on flood risk at the larger spatial scales. So this work, at least to start with, is predominantly field-based. So this is the overall kind of experimental design that we used. And the key here is to think about the processes that link soil compaction to runoff generation. So we wanted to measure all along that kind of process continuum to think about, to kind of quantify the links between them rather than just having cause and effect that aren't directly related to one another, or might not be directly related to each other. So firstly, we quantified the level of compaction in these fields, and this was predominantly done using a dynamic cone penetrometer that you can see there. And this works by dropping a weight of known amount onto the spike that goes into the ground and measuring how deep it goes. And we use this in two particular ways. Firstly, measuring the depth at which the first hit went down, because we could get lots of data and repeat that several times to capture that spatial variability. And then also fewer ones where we went down to 25 hits to see how far the spike went into the soil to quantify the soil compaction at much deeper levels. And the next kind of step on this is to quantify the physical soil properties in these same areas. So we did this by both in the field and also in the lab as well, by taking soil cores. And these cores were collected and we tested these for a range of different things. Firstly, the bulk density, which relates to the porosity of the soil. We also quantified the particle size distribution and the organic matter content of these samples as well. And then finally, we wanted to link this to how water interacts with the soil. So again, we did this both in the field and the lab. So in the field, we used soil moisture probes to quantify the soil moisture level. And also we did double ring infiltrometer experiments in the field as well. And then we used the same cores that we collected for the soil properties to test the saturated hydraulic conductivity of these samples, which is basically a measure of how quickly water passes through those samples, thinking about the connectivity between the different pore spaces in the soil. And it's hoped by collecting data at all of these different levels of the hydrological cycle that we can start to relate the cause, compaction, to the effect, which is increased localized water runoff. And we used various sampling strategies to quantify this at the field scale. Firstly, we chose particular areas of fields that we assumed would be more heavily compacted than others. So this was in pastoral fields with horses, sheep and cattle. Those are the three animals that we found fields for. And in those fields, we assessed the area around the field gate, shelter areas, and also around feeding troughs as well. And we also collected the same data in an open field area, which we assumed would be less heavily compacted than the previous three locations. So once we'd done that work, we built upon that because each of these localized samples were taken at a 1 meter square around these different features, and we took 25 samples at each of those points. But we built upon this by doing a continuous field scale strategy as well, by collecting points along this grid here. And we did this at different spatial scales, as what you can see there. So a high level over the whole field, but then more detailed values at particular points in those fields as well. And then what we wanted to think about how representative these fields were of the overall catchment. This work for the River Sense in Leicestershire, we collected both pastoral and arable samples across the whole catchment to quantify the differences in these soil physical properties. So now I want to show you some of the results of this work. Firstly, the top part of that, thinking about these 4 different areas of fields. So the open field area, the feeding trough area, the field gate, and a tree shelter area in each of the 3 fields, cattle, horses, and sheep areas. And I want to do this for across the whole process continuum, linking soil compaction to the hydrological processes that are happening. So the first type of data that is presented here is the dynamic cone penetrometer data from 1 hit. Okay, so the weight was dropped a single time, 25 times within that meter squared area. And we quantified the depth at which the spike went into the ground. So if it didn't go in very far, therefore low values of penetration, then they are indicating areas of higher compaction. And if it goes in deeper towards the top of this graph here, that's indicating areas of lower compaction. Just to identify the different characteristics for the cattle field to begin with. So we found that the area of the open field had overall an average and distribution higher, so areas of lower compaction there. But also a very wide distribution as well, covering the whole range of values that you can see here with these outliers. And that we're thinking is caused by the animals trafficking over the field and following particular paths through the field, which we might not have been aware of at first. But also then thinking about different areas of the field as well. So the depth of penetration is the lowest, indicating the highest levels of compaction around the field gate area. We did the same thing in the other 2 fields as well, and you can see the comparison of these distributions. Often the tree shelter area has the highest compaction in the sheep and the horse fields there. But what's interesting about this data is that the trends between the 3 different fields is less significant than the within the same field variations, and that's indicating that soil physical properties vary at very small spatial scales, and that it's important to think about this when we're thinking about how water rainfall might interact with the soil. Just showing some other data. This is now just for the field with the cattle in. Just some other data that we used. We analysed the penetration data, and we can calculate the overall penetration depth. So this is when we have 25 hits of the penetrometer. And what you can see here is that the area where the lowest depth is reached, indicating higher levels of compaction, is this time for the tree shelter area. So that might indicate that at greater depths in the soil, that zone is more heavily compacted, when at the surface level, the field gate was the most heavily compacted area. And that is backed up when we calculated the penetration resistance. And we did this at different depths in the soil, but this data here shows at 150 millimeters depth, so very shallow depth in the soil. And this indicates that the field gate area has the highest penetration resistance value at that shallower depth. But then when we quantified the overall penetration to much deeper levels, the tree shelter area results in this lower depth overall. So that's interesting in terms of the depth at which these different areas of the field are experiencing soil compaction. We went on to analyse the soil cores collected from these different areas for properties like bulk density, which is shown on this figure here. Firstly, for the in the cattle area, the field gate showed the highest bulk densities, and so these soil cores were taken from that surface layer of the soil, approximately 5 to 7 centimeters of depth, and that kind of confirms the same conclusion that we found in the first type of penetration resistance data that we've just gone through. But you can also see differences in the different fields as well. So the tree shelter area has the lowest bulk densities at that surface layer, but like we were saying before, might be more heavily compacted at deeper levels. In the sheep field, again, the field gate has the highest levels of compaction, fairly similar to the cattle field, whilst the other 3 areas of this field were similar to one another and weren't statistically different to one another, whilst the field gate was statistically different. And that's interesting because the open field area that we assumed to have a lower bulk density did, but also other areas of that same field had similar bulk density values. And then for the horses field, we can see these 2 clusters really of the feeding trough and the field gate having higher bulk densities when the open field and the tree shelter area had lower values of bulk density, where within those clusters they weren't statistically significant, but between them they were. And just displaying that data for the cattle field alone this time, but in a slightly different way to look at the overall distribution. You can see here, so on the x-axis we have the bulk density values, and on the y-axis we have the percentage of the samples, the 25 samples that were collected. And what you can see here is that the field gate data had by far the highest bulk densities, practically all of them being greater than 0.95 grams per centimeter cubed, when the other 3 were more similar to each other, where the feeding trough was the second highest, and the tree shelter area having the lowest bulk densities in this particular field. And from this, we can extract metrics such as the 50th percentile, the median value, for example, and see how that differs considerably between these 4 different areas of the same field. So the final bit of data for this study that we did of these 4 different zones of fields was to think about the impacts on the hydrological processes. And this started by thinking about the permeability of the soil. And this was measured through the falling head test for the saturated hydraulic conductivity, measuring how easily it is for the water to pass through these soil cores in the lab. And what you can see from this data here is slight differences from the data that we collected on bulk density and penetration resistance, where the feeding trough area has the lowest KSAT value, indicating that water is passing through the sample at a very low rate. When the other areas of this field were much higher, and the highest of which in terms of its median value was the open field part of that field, of the cattle field. But interestingly, when we moved to the sheep field, there was far less variation in the permeability of these soils across these four different areas of that field, where none of these were statistically different to one another. And then in the horse field, similar to what we've seen in some of the other data, we had these clusters of the feeding trough and field gate areas having lower values of KSAT, and the open field and the tree shelter area having much higher, statistically significantly higher values for the permeability of the soil cores. And then we also measured the soil moisture levels, both in the field, which is this data that I'm presenting here, but also in the lab environment as well, to see how different these two methodologies were. And you can see differences both within and between these different fields again. So within the same field, we can see that all sites are statistically different to one another for the cattle and horse fields. So they showed the greatest amount of variability in the soil moisture values, often with very little overlap between the whole distribution of these different areas in terms of the soil moisture, where the open field area in the cattle field was by far the driest part of the field, and the other areas were much wetter. And then the tree shelter area is the driest part of the horse field, and the field gate being the wettest. When in the sheep field, again, that had the lowest value for the tree shelter area, but this the other three components of that field were very similar to one another and not statistically different to each other. And then when we think about the differences between the different fields with different animals in, we can see that for the open field and for the gate area, these are statistically different to one another in terms of each of the three fields, where the horses has the highest value for the soil moisture, and the cattle field had the lowest soil moisture. But there weren't any differences between the feeding trough areas between these fields. So those differences weren't statistically different to one another. So what it's useful to think about here is where there were similarities between these different areas of the field in terms of levels of compaction linked to areas of high bulk density, and then also where the KSAT and the soil moisture values corresponded to those more compacted areas. But there were also discrepancies across those continuum of that kind of linkage of these cause to effect as well. And those are probably caused by these local characteristics, along with not always understanding where the trafficking areas of the fields were. So to try and collect more data on this, rather than at that very small 1 meter plot scale, we collected data across the whole field. Obviously, this data was at a much lower resolution, but it allowed us to identify areas that were similar and different to one another across that whole field. This part of the work was done for the river sense rather than the previous work done in the Skell catchment in Yorkshire. And this field was a cattle field, but we also did it for the other types of pastoral agriculture, which I'll come in onto on the next slide. So in this, we collected the same types of data, trying to link the levels of compaction to the hydrological and physical properties of the soil. So if we look at the first plot there of the bulk density, we can identify areas of low bulk density shown by the blue areas in the center of that field at the top there, and also areas of much higher bulk densities as well. And this just indicates that there are large spatial variabilities and zones of more heavily compacted areas within that same field. And thinking about what the consequences are for upscaling this is what we'll move on to in the final piece of work. We also collected data on the penetration resistance. So you can see, so this was collected in the same methodology of the dynamic column penetrometer. And you can see on this, so areas in blue have low penetration resistance values, and yellow areas have the highest penetration resistance values, indicating more heavily compacted areas. And what you can see there is that there isn't always a strong correlation, a strong spatial correlation between the bulk density and the penetration resistance. So, for example, the big blue area that I pointed out in the bulk density value, having low values of bulk density, indicating low levels of soil compaction, came out as having high values of penetration resistance, indicating higher levels of compaction. And some of this might be to do with the depth at which these were measured at. So the bulk density was only a very surface measurement, when penetration resistance accounts for a much greater depth in the soil column. But also there are it occurs in more areas of that field than just that one as well. So these physical properties of the soil don't always correlate with one another. And that follows through to thinking about the water content, the soil moisture level, which you can see at the bottom left plot there. But there was much less spatial variability in the soil moisture levels across that field than in some of the other characteristics. So typical values were around about kind of 35%, with the area of lower bulk density having the highest soil moisture levels. And when we're thinking about the relationship between the soil compaction and the moisture content, we need to think about two different components. Firstly, the storage capacity of the soil to hold on to water, which might be less in compacted areas, but also for water to pass through the sample, pass through the soil as well. And for both of those reasons, we might get different moisture levels. And then the saturated hydraulic conductivity data, which was again measured in the lab and at a much lower spatial resolution than the other types of data that were collected in the field, indicates again that these areas don't always correlate with each other spatially, and highlights the importance of other factors, both natural and also other components of thinking about how land management affects the soil characteristics as well. So moving on to thinking about different types of animals, you can see the spatial variations for these different pastoral agricultural systems here. So we have the sheep field having by far the lowest bulk density values in comparison to the highest, which are in the cattle field. And that follows through to thinking about the penetration resistance as well, but for this time when we had much greater levels of variability at greater depths within the soil layers. Just to give a little bit of data on the catchment scale work that we did as well, where we introduced arable land uses as well and compared them to the pastoral fields. You can see in terms of bulk density there that the arable fields had higher bulk density values. They were statistically different to one another. And also the penetration depths for the first, second, and third depths were also different for these two different types of agriculture, indicating that the pastoral field had less compaction in them, going to greater depths. The KSAT values again followed through where the areas of greater bulk density had lower KSAT values. Again, these were statistically different to one another. So just to summarize this, the field aspect of the work, we found that the soil properties were highly heterogeneous and that there was the same level, if not more, variability within the same field as between them. And we produced these spatial maps of these soil properties to identify these zones of compaction and different soil characteristics. But it's important to note that these weren't always highly correlated with one another, showing the importance of other factors beyond the land management practices in influencing the soil properties. So what I want to move on to now is thinking about what can occur at the catchment scale. How important could soil compaction be at the catchment scale in causing different amounts of flooding or high water levels? And to do this, it isn't straightforward. So this is the problem of upscaling, where we can't just simply extrapolate from the plot scale to the catchment scale. And that's due to three main reasons. Firstly, that as we get further away from where the intervention is, the impact of it reduces and is attenuated as we move downstream through the river system. These different fields are in different areas of the catchment, they're diffuse, and we need to understand their combined effect rather than their effect individually, which will interact with the stream network in different ways. And also we have different land management practices occurring throughout the catchment, some that might increase runoff, some that might decrease it. And again, we need to understand how these amplify or balance out at the catchment scale. So to do this piece of work, we used a hydrological model, a physically based hydrological model called CRUM3. So this is kind of a schematic of its 1D process representation. And we can route water through the catchment, both over the surface and in subsurface, to give us discharge at the downstream point. And we ran different scenarios of compaction through this model for a whole year that I'm presenting the data for here, where there were two main flood periods, or the main one there in the January time. And we ran these three scenarios, which are presented here, but I'll also show more data in a few minutes. And what you can see is that as we increase the level of compaction, the peak flow, the highest discharge, increases considerably. And what we can see is that the difference between low levels of compaction and high levels of compaction is around about 65% from this data. And the plot at the bottom shows how we studied this as a continuum, a linear continuum across the x-axis of the level of compaction. And what's interesting here is that it's not a linear trend, it's where we get a tipping point occurring where we have this jump in the peak discharges downstream. And we see the same for the low flow periods, where there is over 80% difference between the low level compaction and the high level compacted scenario. So what we can do in this model is we can start to not just look at the output of the model in terms of discharge, but we can look inside the model, looking at the different hydrological processes that are happening in the model itself. This graph here shows the continuum of compaction on the x-axis as before, and then on the y-axis we have the percentage of the rainfall that is partitioned into the different stores and fluxes within the soil layers. What's interesting here is that if we look at the red line here, which indicates the total runoff, we can see that as we increase the level of compaction, the total runoff decreases from 77 to 65%. And that's kind of counterintuitive to what we would expect. But if we look at the proportion of that occurs on the surface, which is a fast pathway of connection to what's happening in the subsurface as water moving through the soil as through flow, we can see that the proportion of through flow decreases from 56% to only 1%. And that means that more of this water is going over the surface and resulting in higher peak discharges downstream. We can also look at the soil moisture saturation levels as well, averaged over the whole catchment. And what you can see here is for the three scenarios, heavily compacted, moderate, and light compaction, the level of saturation over this whole time period. And what you can see here is that for the heavily compacted scenario, the blue line, the soil is nearly always saturated. It never goes below 0.95, 95%. And for a lot of the year, it's at full saturation. For the moderately compacted scenario, it reaches saturation during those two main flood events in the January and the November of this year. It gets up to those very high saturation levels. But for the rest of the time, it's much less saturated. And then for the lightly compacted scenario, it never reaches that level of saturation. And that's why, if I just go back to this graph here, is that you see this big difference between the light compacted scenario and heavily compacted scenario. But the difference between moderate and heavy is very small. It's insignificant, that difference. And that's because the soil is saturated in both of those scenarios, resulting in rapid overland flow. So yeah, that difference between moderate and high only being 3.7% caused by that soil moisture driving that flood generation downstream. As we upscale from the subcatchment of Dacre Beck, where this work was done in the Lake District, 36 kilometre of that catchment was modified for these different soil compaction scenarios. As we then use a hydraulic model to upscale this to the full Eden catchment and also the subcatchment of the Emont, we can see how that difference between the heavily compacted scenario and the low compacted scenario decreases considerably in terms of the peak discharge. 60% in the relatively small Dacre Beck catchment, and as we upscale that, it reduces to only 3.5% difference in the whole Eden catchment. This indicates that it's important to think about where we do things in a catchment to think about what effect it might have. I'll just skim through that so that I can just talk about the final piece of work that we did, where we used this hydraulic model for the Eden catchment to think about why we should target NFM in particular parts of the catchment rather than doing it uniformly and opportunistically across the whole catchment area, because it can have quite different effects on the peak discharges downstream when it's done in different areas. So this used a hydraulic model where we shifted the input hydrographs from the 5 different subcatchments, both in terms of the timing of the flows and also the magnitude of the flows as well. And then we can assess what the impact is downstream. So if we first consider the magnitude of this, of the flows in the different tributaries, we can see that some subcatchments contribute much more to the peak flows and flood levels downstream than others. So if we change the discharge by different percentages on the x-axis here, we can see the reduction in the water level on the y-axis there. So if we change things in the upper Eden catchment, that's the one where we're seeing the biggest reductions in water levels downstream, around about 30 centimetres. But other subcatchments like the Petrel had very little impact. But more interestingly, is thinking about the timing of these flows as well. So this figure here, on the x-axis, we have the time shift, where moving in one direction, we make the flood peak earlier in the subcatchments and tributaries, and the other way, we delay the flood peaks. And what we can see here is that for the 2 upper parts of the catchment system, the whole Eden catchment system, the Emont and the upper Eden, we need to delay those to see a reduction in flood peak downstream. But for the Coldew and the Irthing catchments, we need to make those peak earlier to see reductions in the peak flow downstream. And the opposite of that would actually make water levels higher downstream if all the other subcatchments stayed the same. So that just is to kind of show how this work can be used to upscale some of these local scale impacts to the catchment scale, and thinking about how local scale variability is important, but also having that knowledge of how the overall catchment system works is important in terms of targeting natural flood management to locations where it might be more effective. So in summary now, we can see that land management can have significant impacts at the catchment scale if it's implemented over substantial areas, firstly. So the whole of Dacre Beck was modified to see the reductions that we saw there. But also it could be locations where NFM is positioned could be targeted to think about the effects as well. The soil physical properties have a non-linear effect on the partitioning of rainfall into surface and subsurface runoff at that catchment scale. And therefore, we need to know what the baseline soil characteristics are to understand whether we might see a benefit in terms of reducing compaction, for example. And then at the very largest scale, so catchment scale, thinking about how these different tributaries interact with each other, particularly in terms of their relative timing and the sequencing of them, because that has an important role to play in terms of generating catchment scale flooding, and therefore we can use that information to target NFM to locations where it might be more effective. And that's all. Thank you.
So we've got 5 minutes or so for questions. If people do need to head off for other meetings and stuff, just feel free. So yeah, I'll give privilege to those in the room. Those on Teams can put up their hands or put something in the chat. I'll come to you. So any questions in the room? So, yes.
Thanks very much. That was really interesting. I suppose it probably poses as many questions as it answers, but I guess one of the things I'm interested in is that subcatchment scale management, because that looks really interesting in terms of being able to target resources to manage those peak flows. So I'm just wondering how easy it would be to replicate that kind of research into other catchments so that you can then target activities. Is that, just to get the idea of scale, is it a massive piece of work to be able to do that at subcatchment? You know, or
So it was done using a hydraulic model, but one that was that we didn't produce ourselves. It was taken from the Environment Agency, who had already got that model, and we just modified it to answer the questions that we wanted to use it for. So we didn't have to collect any of the cross sections or any of this kind of thing. It was already kind of there for us to kind of tailor to this particular question. So in that respect, it could be easily replicated in other areas if a hydraulic model of this kind exists already, or if not, it would be a little bit more time consuming to do. I also did a piece of work where we, so that was just for one flood event, and obviously the interaction of different tributaries might differ in different flood events and so on as well. So to account for that kind of work and impact, we looked at, I think it was about 150 events, but we looked at that in a statistical methodology rather than a hydraulic modelling methodology, where we identified which subcatchments were most important in terms of their magnitude and their timing in terms of contributing to downstream flooding. And we found the same result, that the Upper Eden was by far the greatest contributor, but obviously there was differences in different flood events, and that means that by using NFM, and if you target in a particular area, you can identify the subcatchment where in most of the events it will have a positive impact because it will desynchronize the peaks and so on. But in a proportion of the events that happen, it will actually make those flood peaks more coincident with each other as well and make flooding worse downstream. So that just shows the uncertainties associated with catchment scale natural flood management compared to kind of flood defences, which will always protect to the same levels downstream. So yeah, quite complicated and so on, but has potential to be replicated elsewhere.
So we've got one question on Teams, and then I'll come back to in the room just because I had their hand up. Shisha, I think you were wanting to come in. So.
Thanks, Tony. Sorry, I should have been in the room, but I had a meeting for this one, and I couldn't dash there in time for the seminar. Thanks, Ian. I was just wondering, as you were presenting, I was thinking about groundwater flooding, and that's because just last week I was in Oxford and we went to a flood management site where groundwater flooding is an issue, particularly for residential areas, and I wondered what some of the impacts, would be from a catchment scale approach like this for particularly residential areas, and if you had any issues with groundwater flooding in the catchments that you studied.
Yeah, okay, so there are obviously links between how much water infiltrates into the soil and how much goes into the groundwater as well. And in the hydrological modelling that we did account for those losses to groundwater, but it was just a loss to groundwater. It never came back out of that store in the particular model that we used. And wasn't a particular focus in the catchment that we were studying. And we were more interested in the kind of surface soil characteristics and the impacts that land use might have on the higher upper layers of the soil. But yeah, definitely thinking about the wider implications of these different land management practices on groundwater storage and therefore impacts on droughts and low flows. And we did see in the results that the impact on droughts was quite considerable again between these different scenarios of compaction. So yeah, that's definitely something that would warrant further investigation. Yeah.
Thanks. And then yeah, there's one final question.
Yeah, when you're doing your species comparison, were you able to control for the stopping density, the difference in stopping density between the species? Because for instance, usually the bet your horses, when you get a field of say a cat or sheep, and also that's going to impact the compaction rates that the various areas of the field.
Yeah, okay, so yes, Yeah. So we couldn't control for it, but we did account for the different land management practices that are typically used. So we collected data about the number of animals in the fields and so on. And we did look at the wider literature about how much pressure their weight exerts on the soil and so on. And yeah, one of the biggest differences is the way in which cattle and sheep are managed is completely different to the horses, for example. So they were typically in smaller, much smaller kind of enclosures. And there were fewer animals in those enclosures as well. So that we didn't control for it, but we did use that information to kind of think about the impacts that it was having.
Thanks. So I think we'll close it off there. It's just kind of a couple of minutes to 2. Ian, are you sticking around for a little bit? So yeah, I think if you want to speak to Ian, obviously come up and see him. We've got the room for a little bit, or again, you can liaise with Alan if there's anything else. So just to leave us to thank Ian for the talk. So thank you very much, Ian. So.